Welcome, everyone. Oh.
Sorry for that.
Okay, so welcome everyone to my presentation called Data Rate Limits for the Remote State Estimation. And this presentation will be given by me, Alexander Pogromsky. And this presentation is based on a recently published paper, this one, which appeared in, I believe, in March in Automarica. So this paper is co-authored with Christoph and Alexei Matveev from St. Petersburg and Munich. Okay, so, and of course, the first things which I have to mention is I would like to thank the organizers for this opportunity to give a talk here directly from my bedroom. And I have to say that this pandemic changed the way we work and communicate. But anyway, it's not only a threat, but also a kind of opportunity, because otherwise it would be quite difficult to give a talk to people from so many continents. Okay, so if I, this is how to control my screen. So this is the outline of my presentation. First, I will present some kind of motivation of the remote state estimation problem. Then this problem will be discussed in more detail here. Then I will formulate the main results in continuous time and in discrete time. Those results will be illustrated by a number of examples. And then I will briefly mention some related results which can fork from the approach which we will discuss here today. And the talk will be finished by the concluding remarks. And as a first slide, I would like to show you the picture of Gennady Lyapunov, who passed away quite recently. And I would like to acknowledge that some of the results which I'm going to present you here today are largely inspired by those books which I selected to show you, where he developed together with his co-authors dimension theory for dynamical systems. And I have to say that even now during the lockdown time, I brought those three books from my office to my home, to my bedroom, because I use them on a permanent basis. Okay, so few words as an introduction. So the modern control paradigm now is shifted towards networks. And now if we hear these two words, control and networks, we can think about two different scenarios. At least I can imagine two different scenarios. So in the first situation, the network agents, like here, 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 and there, they're mutually interconnected and they exchange information, exchange the control action in order to achieve a common control objective. And this control objective could be, for example, consensus or synchronization. And in the second scenario, the main ingredients of the networks, like sensors, actuators, controllers, they exchange the information via communication network, for example, the internet. And in both situations, limited data rates between the communication peers can degrade the performance of either network or control system. And to cope with this issue, the control design has to take into account possible data rate limits between the agents. And this is the subject of my presentation here today. And a possible approach or abstraction of the control problem here is the so-called control problem over communication channels. And in this framework, sensors, actuators, and controllers, they're interconnected via communication channel with limited data rate. Yeah. And the goal is to achieve the desired behavior in the control system are the limitations imposed by the communication channel. And in this talk today, we are going to focus on a particular subproblem, which is called the remote state estimation. Yeah. So we will assume that there are two speakers or agents, peers, communication peers that communicate via the communication channel with limited data rate. So the first channel, agent has a full access to the system state called X. And this agent communicates with the second agent via communication channel with limited data rate. And this peer sends the messages from a finite alphabet to the second peer, and the goal of the second peer is to end up with a reasonable estimate X hat of the true value of the state variable X. So the goal is, by means of communication via a limited communication channel, to achieve that the estimate of X is sufficiently close to the true value. Okay, and here I mentioned some papers which you can read to learn more about the remote state estimation problem. And of course, I'm sorry that the list of the papers is not complete because the margins of my slides are too narrow to present here a comprehensive list of the papers. Yep. Okay, so probably the simplest way to address a constrained communication problem is to introduce so-called zero-order holder, which is quite familiar to all of us who are busy with control practice and theory. So this zero-order holder takes the values of the input which are sampled in time, and also in space. And the accuracy of the discretization together with the sampling frequency determine the bit rate at which the data are sent from the transmitter to the receiver. And it's well known that the sampling frequency cannot be smaller than the so-called Nyquist frequency, which dictates that in a period of the transmitted signal, there should be at least 2 samples. Yeah. And the zero-order holder is quite easy to implement. And from a dynamical point of view, it's characterized not only by the bit rate, but also by the latency. And this latency is given by the time interval between the transmission and receiving a package. Yeah? And this delay can impact the stability of the control system, and even worse, the situation can be even more complicated if this delay, transmission delay, is not constant. So the main advantage of the zero-order holder is the ease of implementation. Yeah, and also this zero-order holder can be implemented independently on the dynamics. Yeah, it's quite a universal way, but of course it's not optimal with respect to the communication rate. And what I mean by saying it's not optimal with respect to communication rate is illustrated here. Suppose in the previous slide, what we have to do is to inform the second communication peer about the harmonic function of time. Yeah. And in order to do that, we have to know only 3 parameters: amplitude, frequency, and phase. Yeah. And suppose those 3 parameters are rational, then they can be encoded by a finite number of bits. And if we are interested in the communication rate, then the communication rate can be 0 if we take a quite long interval of communication. And at the same time, if we approach the zero-order holder scheme, then the communication rate can be quite substantial. Yeah. And what I presented here is just a way to encode the information about the signal which we want to deliver to the receiver. And there are many, many other ways to encode this information. And in this talk, I'm going to pay more attention towards optimal encoding, optimal with respect to the communication rate. Okay, now let me pose the problem of remote state estimation in a more formal way. Suppose we are given a dynamical system which evolves in discrete time. And what is known about this system is that there is a set K, set of admissible initial conditions, and we know a priori that only initial conditions from this set can be taken into account. So this capital K is a compact and forward invariant set. So the initial mismatch between the true value of the system state X and an initial guess X hat is known to be no worse than delta. Yeah. And there are two important components in our communication scheme, the coder and the decoder. So what do they do? The coder generates the signal which has to be sent via the communication channel. This signal is called E, and this signal E takes values from the finite alphabet. Yeah. So the initial guess X0 hat and delta from here are the parameters of the coder. And also coder has the full access to the state variable X, and for example, in a recursive way. And those parameters and signals are used in order to generate the signal E from a finite alphabet, which has to be squeezed into the channel capacity C. And the channel capacity C is defined as the number of bits which the channel is able to transmit up to time t, divided by t when t goes to infinity. And we assume that this limit is well defined. Yeah. So the decoder performs a sort of inverse operation to the coder. So given the time history of messages which are squeezed into the channel, the decoder has to end up with a reasonable estimate X hat of the state X. And reasonable in the sense that the distance between X and X hat should be relatively small. And this requirement that the distance between X and X hat is small can be interpreted in different ways. Yeah. So depending on a particular meaning of this constraint, we can distinguish different types of observability via channels with communication capacity C. Yeah. And now I'm going to demonstrate you how this requirement that X minus X hat should be small can result in different concepts of observabilities. Yeah. Okay, suppose that the channel capacity C is so large that I can find a coder and decoder which enjoy this property. So for any epsilon, I can find delta so that if initial mismatch is smaller than delta, then this distance in future is smaller than epsilon. Yeah. If this is the case, we say that the system is observable via the communication channel with capacity C. Yeah. In a similar fashion, we can define the notions of fine and regular observability. So briefly, there should be a constant capital G and small g so that initial mismatch smaller than delta results in the future that difference between x and x hat decays in an exponential way. Yeah? And this should be true uniformly for all delta smaller than some threshold. And if this quantity small g is chosen to be 0, we say that the system is regularly observable. And again, given a capacity C, we can find a threshold which guarantees observability, regular observability, and fine observability. Threshold in the sense that if the capacity is above that threshold, for sure we can guarantee regular, fine observability, or observability. And those thresholds can be different. So one of the intermediate results is that if K is forward invariant and compact, the regular observability rate and fine observability rate are the same. But in general, they can be different from observability rate. And in this talk, I'm not going to discuss the pros and cons of these different observability concepts. What I would like to mention is, look, here, the observability notion is quite close to stability. And fine observability is close to exponential stability, at least in spirit. And of course, we know from nonlinear control theory and practice that the notion of exponential stability is superior over asymptotic stability if robustness matters. And similar situation holds also true for to underline the difference between fine observability and observability. But details, however, are outside the scope of my talk. Okay, and before I show you some mathematical statements, I would like to discuss how the transmission data can be encoded and decoded. Yep. Okay, suppose for a while that this little young lady is willing to go to Rome. She doesn't know what route to choose, what route to select, and there are plenty of options, and that's why she asked for an advice. And it seems that there are many possible routes, and if you count all the roads from 1 to capital N, then the answer will give her a logarithm of n, or binary logarithm of n, bits of information. And at the same time, if she knew a priori that all roads lead to Rome, then any answer is redundant and contains 0 bits of information. Yeah? In a similar way, as Shannon said, yesterday's newspaper contains no information. So information is a kind of measure of uncertainty, like, okay. And this simple observation shows that the coders have to focus on the uncertainties and to exploit as much as possible the knowledge which is a priori known to both communication peers, the coder and decoder. And in our situation, yeah, if we talk about observability, then in our situation, the uncertainty is caused by the initial conditions. Yeah. And the system dynamics is assumed to be known a priori to all the communication peers. So, in order to make my demonstration accessible, suppose we have 2 communication peers, Alice and Bob. Those names are typical in cryptography. That's why I use them. So Alice has to inform Bob about the solutions of these dynamics. And we assume that both of them, Alice and Bob, are aware of those equations. Yep. So Bob knows the initial condition x0 with some uncertainty. And this uncertainty is depicted by a ball of radius delta. And Alice knows what Bob knows. And even more, she can measure trajectory of our system at any moment of time. So the question is, how to design a communication protocol between Alice and Bob in such a way that Bob knows the value of x with the accuracy no worse than delta at any given moment of time in future. Yeah? That's our problem. And now how a way to solve this problem. So given the ball of initial uncertainty delta. So Alice can evaluate the image of this ball under our dynamics. Yeah? And since this dynamics is also known to Bob, he can perform absolutely the same calculations to end up with the same sausage-like set. Yeah? The next step in the communication protocol could be to slice the sausage into pieces with the size no more than the initial ball. And again, this could be a part of the communication protocol, and Bob can repeat the corresponding calculations to end up with the same figure. So Alice knows that the image of this point x0 falls in the blue ball, yeah? Somewhere here. All those balls which appear here can be indexed from 1 to capital N. And this indexation procedure is also a part of the communication protocol and can be repeated by Bob. Yeah. So what we have to do now, or not we, but at least Alice can try, is to inform Bob about the index of the ball, blue ball, which contains the image of this point. Yeah. And what about the amount of information in terms of bits which we have to send, Alice has to send to Bob? This is logarithm of n, okay, or binary logarithm of n. So once Bob receives this index, he knows that this ball contains the image of the initial point. And then history repeats itself. So therefore, for any moment in future, the estimation accuracy will not explode. It will be no worse than the initial value delta. And after such an informal motivation, it's time for me to give you a mathematical definition of a quantity which we called the restoration entropy. Yeah. I remind you that phi here is the mapping which has a forward invariant compact set K. So now given a ball, delta ball, which is centered at point A and denoted by B with index A and delta, what we try to do is to intersect this ball with the set of initial conditions, K. And then for a given quantity T, time interval, we try to evaluate this set. And this is nothing more but the sausage which appeared here. Yeah. So this is nothing more but the mathematical description of that sausage-like set. And then, similar to what Alice and Bob did, we try to find the minimum number of delta balls which are required to cover this sausage. What we do next is to try to find how many bits are required in order to encode the capital N. So we calculate binary logarithm of capital N. Then we maximize that quantities for all a's from a given set of initial points. Then we try to shrink this ball, radius of this ball to 0, and try to find the average value when t from here goes to infinity. Yeah. And this value is what we called the restoration entropy for a given dynamics phi and a given set of initial points, capital K. And it can be proven that this outer limit, upper limit, is well defined in a strict sense. Yeah. Okay, this is about the definition of the restoration entropy. And now I would like to summarize some properties of the restoration entropy. So first, it can be proven that the restoration entropy is an upper estimate of the topological entropy. Yeah. Then we can pose a question. What about this inequality? Is it can it be strict, or maybe there are some systems for which the topological and restoration entropy are the same? And the first result is presented here, where we prove that for a logistic map, the topological entropy is strictly less than the restoration entropy. So those quantities are indeed different. And second, I would like to mention this result proven by Christoph Kavan. And without going to details, simply it means that strict inequality in this estimate happens more often than equality. And for details, look at that paper, because details are outside the scope of my talk. So how those quantities, restoration entropy and topological entropy, are related to the state estimation problem? Yep. So the restoration entropy gives us a threshold for the channel capacity, which ensures regular or fine observability. I remind you that if the set K is forward invariant and compact, the regular and fine observability rates are the same. And exactly the channel capacity which ensures fine observability is nothing more but the restoration entropy of our system. At the same time, we know that the topological entropy gives a threshold for mere observability rate. So what we know is that if you give me dynamical systems, then most likely the observability rates and which ensure observability and fine observability, then they're different for, how to say, given systems. So most likely for a given system, fine observability requires a larger communication rate than mere observability, because the topological entropy is strictly smaller than the restoration entropy. Okay, and to formulate the main result, first I present a way to find an upper estimate of the restoration entropy. Yeah. Okay, given mapping phi, let A stands for its Jacobian. Then P is a probably state-dependent positive definite matrix. So now for given A and given P, I try to solve this algebraic equation. Yeah? A transpose P, which is related at the next value of x minus lambda P at the point x. And I try to solve this algebraic equation with respect to lambda. Yeah. So those lambdas will be non-negative because this is nothing more but generalized singular values, and they cannot be negative. And what I'm doing is I calculate the square roots of the solutions of those lambdas. And those square roots are denoted by alpha. Next step to do is to take a binary logarithm or maybe a natural logarithm of alpha only if that alpha exceeds 1. And then we sum over all possible alphas and maximize this quantity over all the initial conditions, admissible initial conditions in K. And what appears in the right-hand side of this formula gives an upper estimate of the restoration entropy, no matter what P is selected. Yeah. And to give you a clue what it means, how some kind of interpretation behind this formula, at least if you're familiar with convergent systems or incrementally stable systems, if for simplicity, suppose A is a constant matrix, which is stable in sure sense. It means that all the eigenvalues are inside of the unit disk. Then it's possible to find such a P that all lambdas are between 0 and 1. And if you put those quantities here, the restoration entropy will be 0. So if our system forgets the initial conditions, if the trajectories will converge to each other, then there is no need to think about the future of our system. It will be certain. And that's why we don't need to communicate in order to inform the remote peer about the future of the system. And the estimation can be achieved with 0 bits, 0 communication rate. Yeah, it's a kind of motivation behind how to use this formula. Again, if A is a constant matrix, and if there are some unstable eigenvalues, what we have to do is to take logarithms of absolute values of those unstable eigenvalues, and the corresponding sum will give me restoration entropy of the linear time invariant system. And it turns out that this approach also works in case of nonlinear systems. Yeah. Okay, up to now, that was about how to find an upper estimate of the restoration entropy. And from the previous result, which I showed you before, we know that this formula from here is also an upper bound for the topological entropy. And the main result, which I'm going to deliver right now, is that this approach can be used in order to find the lower estimate of the restoration entropy. And in what sense? So if I take an epsilon, no matter how small it is, it's possible to find a matrix valued function P, which is positive different matrix, state dependent, so that if I perform all the calculations which I showed you here, and if I plug the outcome here, then the corresponding value will be epsilon close to the true value of the restoration entropy. So this approach is capable of providing tight estimates of the topological entropy. Yeah. Okay, what I showed you before is about the discrete time. And now a similar result, but in continuous time. So given system of differential equations, again, it has a capital K as a compact forward invariant set. Capital A here stands for the Jacobian of the right-hand side. And now I'm looking for solutions lambda of this algebraic equation. And here, P dot stands for the time derivative of the matrix P along the solution of my system. So those solutions are denoted by sigma. And similar to the procedure which I showed you before, we try to find only those sigmas which are above 0. And then we sum them together, maximize overall possible x in k, and multiply by this factor which depends on the value of logarithm of 2. So for example, if in definition of the restoration entropy, instead of binary logarithm, we take a natural logarithm, it will be 1. And 1 over 2 here appears because in the discrete time, we worked with the square roots of lambdas. Yeah. Okay, so this quantity gives me an upper bound for the restoration entropy for this system of differential equations. And similar to the discrete time case, the same procedure can be used in order to find lower estimates of the restoration entropy. In what sense? So no matter how small epsilon is, for that small quantity, it's possible to find a matrix valued function P, positive definite, so that if I plug this P into this formula, the outcome will be epsilon close to the true value of the restoration entropy. Yeah. So we are able to find estimates by this procedure. So instead of, so basically what we have to do is to solve a number of algebraic equations and to perform a sort of optimization procedure. Can be tedious, but still doable. And in the paper...
Sash, may I interrupt you?
Yeah.
It seems that this Lyapunov-like equation in the continuous time has some p dot, and in the discrete time I have not seen this.
Okay. So indeed, in continuous time there is a p dot, and in discrete time you see here p depends on the value of x at future. Phi here is the mapping. So it's again Lyapunov-like stuff, but in discrete time, P here is evaluated at the next value of X. Yeah.
Okay, thank you.
But of course, it plays the role of P dot here. Yeah. So absolutely the same way of thinking. So both continuous and discrete time, and in the paper which I mentioned in the title page of my talk, that you can find details. Sorry, before going there, I rephrase the main result for continuous and discrete time in this way. So given discrete time dynamics, yeah, given matrix valued function P, I try to calculate solutions of that algebraic equation, take square root of them, which are denoted by alpha, plug it here, and then I try to minimize this quantity with respect to all possible matrix values, matrix functions P's. And this quantity gives me the value of the restoration entropy, which in turn gives me a value of the fine observability rate. And a similar approach can be used also for continuous time systems. So given these dynamics, then given P, I try to calculate algebraic solutions of these solutions to this algebraic equation. Those solutions are denoted by sigma. I plug them here and try to minimize this quantity with respect to all possible matrix values P's. And the outcome gives me the value of the restoration entropy for this continuous time system. Yeah, so this is the main result, which I'm going to show you here today. And now you know that those two quantities give me the threshold of the fine or regular observability rate. And in the paper which I mentioned to you in the title page of my talk, or slide, you can find some details of calculation for restoration entropy for this system. Yeah. So this is a third order system, nonlinear. And it turns out that its restoration entropy is given by this formula. So it depends on the parameter A, which appears in the right-hand side of my system. And in order to prove that indeed this quantity gives me the exact value of the restoration entropy, the matrix valued function P is chosen in this way. So it's a product of a diagonal matrix P times a function which indeed depends on the system state Z. So if you plug this matrix P into the formula which I showed you before, you can prove that the value of the restoration entropy is indeed given by this outcome. Next, I'm going to show you a number of examples for which we are able to find tight estimates. So we are able to formulate the conditions on the set of initial condition K and the system parameters such that the value of the restoration entropy is known exactly. And now I would like to show you that for this system, for Lorentz system, for this example, and for Hennen map, so all the calculations are essentially borrowed from the calculations which were performed in the books of Professor Lyapunov. So basically, if you know how to estimate or to give an exact value of the Lyapunov dimension, which in turn is upper bound for the Hausdorff dimension, then similar calculations could be repeated in order to give an estimate of the restoration or topological entropy. And it's also quite interesting to look at this system, which is a logistic map. So for this system, for this map, the value of the topological entropy is known if the parameter here, which appears in front of x, it's 4, only in that case, the value of the restoration entropy is known as an outcome. It will be 1. If you change 4 to some other quantity, for example, 3.7, then the value of the topological entropy is unknown. Even more, to prove that the value of topological entropy depends in a continuous fashion on the parameter was quite a problem with the long-standing history. At the same time, if we replace 4 by parameter r, then still to find the value of the restoration entropy is relatively simple procedure. So by means of those examples, I would like to illustrate that to find the value or tight estimate or exact value of the restoration entropy is a feasible problem. And at the same time, to find a good estimate or exact value of the topological entropy seems to be either too complex or sometimes even infeasible. Yep. So now I'm going to show you some other papers which fork from the main result which I showed you before, or at least which can follow a similar procedure. And today I don't have time to go into more details, but at least the approach is quite similar. So in this paper, which was published recently in the Transactions on Control, we pose the following problem. Suppose our system is a huge network, and it's so large that the application of the approach which I showed you before is infeasible. Simply the mapping phi or the right-hand side of our differential equation has huge dimension. At the same time, suppose we are able to decompose our network into a form of communicating systems, subsystems, and each subsystem has its own input and output. And would it be possible to exploit input-output relations of those subsystems in order to end up with a reasonable estimate of the topological restoration entropy of the whole network? So it was the problem. And since we are looking at input-output relations, it's not a big deal to figure out that indeed in that situation we can use something like a small gain theorem. And in that paper, we indeed used a small gain theorem approach to estimate the restoration entropy. In that paper, the focus was a little bit different. So in the communication protocol, similar to what Alice and Bob did, if at least one message is lost, then Bob has problems in understanding what's going on with the system. So the communication protocol which I showed between Alice and Bob is very, very sensitive with respect to communication dropouts. So one can pose a problem. Would it be possible still to solve the remote state observation problem if we allow for messages to be lost? So indeed, the modification of the approach which I showed before gives us a higher estimate of the communication rate, but still it's possible to solve the remote state observation problem. So here also I would like to mention a recent result published together with Christoph. And the problem there is also quite, I think, important. So suppose the dynamics either in continuous or discrete time is given. So would it be possible by some kind of numerical procedure to end up with a numerical estimate of the matrix P, which appeared in the main result? Because if we know how P depends on X, then the procedure of encoding and decoding scheme can be generated numerically. Yeah, for example, by that gadget, which ends up with a good implementation of the coder and decoder scheme. So at least for practical application, it seems quite important problem. You simply, based on the dynamics of the system, you can, in a more almost automatic fashion, generate the code of the encoder and decoder. And also, finally, I would like to mention a paper which was recently submitted for publication, where we looked at consensus problem between the agents. So we have a network of communicating agents, and each agent is described by a nonlinear system. And the goal is, by means of communication, to achieve synchronization or consensus in the whole network. And the way the problem was solved is quite similar to the communication protocol described in the beginning of my talk, what Alice and Bob did. Yeah. So now it's time for me to summarize my talk. So I presented you way to estimate the restoration entropy. At least I formulated the data rate theorem, which claimed that the restoration entropy gives a threshold of what is called fine or regular observability rate. Yeah. So the kind of threshold which guarantees solution on the state estimation problem with exponentially decaying mismatch between estimate and the true value. Yeah. So how to find those estimates is a procedure which is at least numerically feasible. Even more, the estimate of the restoration entropy can be made as tight as we wish. So probably to find a better and better candidate for the matrix P which solves the problem, we can use some kind of artificial intelligence approach, deep learning, whatever. So it's kind of subject of the problem which is quite interesting to look at. Yep. And also I demonstrated you that the approach is capable of providing the tight estimates. So for a number of examples, it's possible to prove that the value of the restoration entropy is found exactly. Yeah, so I think this is one of the important conclusions from my talk. And finally, I have to show you some acknowledgement, and all of us are happy to acknowledge those sources for financial support. And thank you for your attention. And of course, I'm happy to answer your questions.